Alrighty, so this is going to be chapter 2. Just going to write it down. Your physics 11, chapter 2, which is going to be your motion. So let me go ahead and start. By the way, you go into module. From module, you go ahead and you go to chapter 2. You click on the class PPT, and here it is. So let's go ahead and start this one. So how do you say an object is moving? Well, first of all, if I tell you how far do you live from here, some of you all might say 5 miles, 10 miles. So you're talking about a distance. Now, if I tell you what time it is right now, it's 2 o'clock. How far away, when you're gonna get home? In like 3 hours. You're talking about time. But how do you say that an object moves? Well, an object moves when it changes its position. That means that object has to be in one place in space at one instant of time, and becomes a different point in space at another instant of time. So if I ask you a question, let's say if I ask you, what is your speed down the highway? Let's say you go down 565, and I call you like, what's your speed? You might tell me 50 miles per hour, 60 miles per hour. Distance over time, miles per hour. And that's where we actually define speed. So speed of a moving object is the rate at which covers the distance. So it's how much distance you go per time. Right? So if I tell you, for example, if you're going 60 miles in 2 hours, how fast did you go? Go ahead and do it. So you probably be like, okay, 10 miles per hour. All right, real fast now. If I tell you, you went 24 miles in half an hour, how fast did you go? Well, if you thought about 24 divided by half, so you go 48 miles per hour. Now, the average speed is the total distance traveled by the object divided by the time taken to travel that distance. So for instance, if you're actually traveling down to your house, you're not going in the same speed the whole time, but how fast did you go? And tell me I was going average about 40 miles per hour. That's your average speed. Now, the instantaneous speed is the object speed at that instant of time. If I call you, like, how fast are you going? I'm going right now, 42 miles per hour. That's instantaneous speed. All right, now we have a little video, and again, these videos are available on the module. Let me go right ahead. Speed, I don't know why it cuts off in the last second. So what is the position between the dots? Tell us about the glider's speed. So is it going up, speeding down, moving constant speed, or any of the above? Go ahead and figure out your answer. Put in your answer, and let's go and look. Notice that the spacing are still equal, but they're further away when you're going at a higher velocity. All right. So now we said the speed equals the distance over your time. We said the speed is your distance over your time. Now your speed, we're going to give it the letter V for velocity. Your distance, your letter D, small d, and your small t, small capital T, is your time. Now, if you solve the equations for distance, V equals D over T. Let me go ahead and solve this over here. So your V equals your D over your T. Your V, that's your speed. D, that's your distance. And T, that's your time. Now, if you solve it for D, cross multiply, what you're gonna have? Your D equals your V times T. Or if you solve it for your time, what you're gonna have is gonna be your distance divided by your velocity. So when you solve for your distance, your D equals your VT. So if I give you a question that says, how far does a car travel in 6 hours? That's equal to 40 miles per hour. So let's go ahead and do the first question over here. So how far does a car travel at 6 hours? It's equal to 40 miles per hour. So your velocity is 40 miles per hour. Your time is 6 hours, and you're looking for your distance. And again, so we derive that distance equals your V times T. So your distance equals your 40 times 6, which is going to be your 240 miles. Is correct. And we already also solved for T. So again, your time equals your distance over your velocity. So if we said, how long does it take to travel 100 miles with 40 miles per hour? Well, let me actually, before I solve that, let me go ahead. All right, so we have to look at the. So let me actually introduce my 4 rules to solve physics problems. So, which I just did a little while ago. So my 4 rules of physics solving. Number 1, you need to write down the information. Number 2, something equals your double question mark. You gotta know what you look for. If you don't know what you look for, you don't know how to answer the question. Number 3, you write down the equation. Number 4, like plug and play, you're just gonna plug the variables and solve. So let's actually do this on the second question. All right, so you get how long does it take to travel 100 miles at 40 miles per hour? Again, so your distance, your first number is 100 miles, which is gonna be your distance. Your second number, that's your 40 miles per hour. So that's going to be your velocity, which is your 40 miles per hour. And you're looking for time. And your V equals D over T, which means your time equals your distance over your velocity, which equals to your 100 divided by your 40. Going to equal to 2.5 hours. Excellent. Now, let's do another question, shall we? You are standing 100 meters north of you, of your car, when an alligator appears 20 meters north of you and begins to run towards you at 8 meters per second. At the same moment, you start to run at 5 meters per second. Will you reach your car before the alligator chases you? All right, well, let's solve this one. What is the first piece of information that you have? So you're standing 100 miles north. So you got, let me go ahead and do this. Number 3. So here's a person over here. And that's their car. Actually, let me just draw a better car than that. And this is our little alligator. That's supposed to be the tail. And let's just give him like a little 2 hands right over here. So here's our little alligator. Now, let's look at the question. So you're standing 100 meters north of your car. So your distance from your car is 100 meters. And the alligator is 20 meters from you. That means he's standing away from the car 120 meters. That means, let's go, 1 is the man and 2 is the alligator. This D1 is gonna equal to 100 meters. Your D2 is gonna equal to 120 meters. Now, the alligator runs at you at 8 meters per second, and you run at 5 meters per second. So the distance, your V1, is 5 meters per second. The alligator is running at 8 meters per second. So we need the time that you get to the car. See, if you get there faster, you're safe. If you don't, you die. All right? Because the alligator is going to eat you. So your time equals your distance over your velocity. So your T1 equals D1 over V1. Your T2 equals D2 over V2. So this is going to equal to 100 over 5, which is going to equal to 20 seconds. And for this one, what you're going to get, D2 is going to be 120 divided by 8, which is going to be 1.5. 1.5 seconds. So man will be eaten by gator. Let's look if we got that correct. Yep, and we got, oh, I'm sorry, 1.5. What did we write? 120 divided by, I have in the calculator 112. Yep, it's 15 seconds. He still dies anyway. All right. Now, we're going to be going through vectors in the next chapter. So we're going to be discussing that in the next chapter later on. Now, but I want to talk about acceleration. Now, an acceleration of an object is the rate of change of velocity, and it is a vector quantity. Now, your acceleration for a straight line is going to equal your final velocity minus your initial velocity divided by your time. So A is your acceleration, T is your time, and VF is your final velocity, and VI is your initial speed or your initial velocity. So let's say a car accelerates from 15 meters per second to 20 meters per second. What's the acceleration? So let me go right ahead. It's question 3. A car accelerates from 15 to 20. So your V initial is 15 meters per second. V final is 20 meters per second. And 20 seconds. Your time is 20 seconds. That means your acceleration, which is going to be your VF minus your VI over T, So this is gonna equal to your 20 minus 15 divided by 20 seconds, which is gonna equal to 5/20. So 25, I'm sorry, this is gonna be 25. This is gonna be, I knew there was something wrong with this question. 10/20. So you get 1/2 meters per second squared. You can just say 0.5 meters per second squared. Now, okay, let me do this. Now we set the acceleration. Well, before I do that. So we said that now we need to find something called delta. Delta V is your final minus your initial, V initial minus V final. Now, for your acceleration, we said it's gonna be delta V over delta T, which is gonna be your VF minus your VI divided by your T final minus your T initial. Which these two is gonna, time minus time is gonna equal to time anyway. So especially if you go from rest, your time is gonna equal to 0. So you get your V final minus your V initial divided by your time. Now, if you solve, so your A equals V final minus V initial over time. Now, if you solve for your final velocity, let me actually go to get a different color on that. So let's say if you solve for final velocity, what you're gonna have? You're gonna have you move this other side, so your initial velocity plus your acceleration multiplied by your time. So this we're gonna call this equation 1. Now we said that the average velocity, your velocity is your distance over your time. That means your average velocity is, let's say x is your distance, so x2 minus x1 over, again, t2 minus t1. Initial and final, I'm just gonna go with t1. Which is gonna equal to x2 minus x1, again, we said it's gonna be equal over time. That means solving for your distance, x2 is gonna equal to your x1 plus your average velocity. Which, again, your average velocity is going to equal to your initial velocity, or V1, I'm just going to stick with 1 and 2 because we've been writing 1 and 2 right now again, plus V2, initial plus V5 divided by 2, that's your average. But we said the final velocity actually, let me go ahead and write this down in 2 and 1s. So your V2 equals your V1 plus AT. I like using 2 1s. So your average, your final velocity, you can go ahead and replace it with this little fella over here. That means your average velocity is going to equal to your V1 plus, go right ahead and put it, at least I can see it, V1 plus AT divided by 2, which let's just break it down. Getting 2V1 plus AT divided by 2. Again, V1 is your initial velocity. So this is going to equal again to 2V1 over 2 plus AT over 2. Oh, what a coincidence. Our twos cancel out. So, and we're gonna get V1 plus AT. So let me go back into red and define this. This is still gonna be equation 1. So, actually, I'm gonna go blue. So your V average is going to equal, we just said, it's gonna be V1 plus AT, oh, we forget the 2. Acceleration multiplied by your time divided by your 2. And again, let me actually write this down over here. A is for acceleration. All right. So your average velocity is V1 plus AT, but we said that the distance, you found this is going to be distance 1 plus the average velocity. So let me actually go get another color. So we can actually substitute this fella with this fellow over here. So let me go ahead and get a different color. Let me go green this time. So let me go write it down. So x2, you said x1. And I guess, let me actually write this down over here. So define these. Show distance, final distance. So x2 is going to equal to your x1 plus average velocity which is going to equal to we forgot when we multiplied this, we forgot to add the t actually. Yeah, I was wondering what was missing from this equation. Yeah, so it's x2 vt minus plus x1. Yeah, that's correct. So this is the average velocity multiplied by your t. So this is going to equal to x1 plus your v1 plus at over 2 multiplied by your t, which is going to equal to, now let's take this fellow over here just to have your delta. So your x2 minus x1 is going to equal to your initial velocity plus at over 2, and the whole thing is multiplied by t. So that means your delta x is going to equal to your v1t plus at squared over 2. Let me actually write this down in red because that's going to be our second equation. So your difference in this is going to equal to your v1t plus at squared over 2. I'm going to give this equation number 2. Now let me go ahead and go back over here. And this is what we just did. So if you actually take the acceleration and which is your final velocity minus initial velocity divided by t, you solve for the final velocity, you get vi plus at. If you solve for initial velocity, you're gonna get vi, final velocity minus at. Or like I like using 2 and 1, so v2 equals v1 plus at. So let's say we have this little question over here. A car whose brake can produce an acceleration of minus 6 meters per second squared at 30 meters per second. What is the car speed 2 seconds later? Okay, so you get your velocity at 30 and your acceleration minus 6. Let me go ahead and write this down. The velocity, should get back to black. So here's another example. So your velocity is 30 meters per second, and your acceleration is minus 6 meters per second squared. And the time is 2 seconds for part A. And it's looking for the car speeds 2 seconds later. So that's your initial, so you need your final velocity. And again, your acceleration is your V2 minus your V1 over T. That means again, your V final or VT equals your V1 plus AT. So this is gonna equal to your 30 plus your minus 6 times 2, which is gonna equal to 30 minus 12, which equals to 18 meters per second. Now part B, what is the car total time needed for the car to stop? All right, so part B, again, what is the total time needed for the car to stop? Well, when you stop, your final velocity is gonna equal to 0 meters per second. That means, plug it in, 0 is gonna equal to your V1 plus AT. That means AT is gonna equal to minus V1, so T is gonna equal to minus V1 over A, which is gonna equal to the numbers. Minus V1, which is gonna be 30 meters per second, divided by A, which again, make sure of the number, minus 6, yeah. Minus 6, so, and this is gonna equal to your 5 seconds, your negatives cancel out. So, if we know the initial velocity, final velocity, acceleration, then we can determine how far an object travels in a given moment of time. And we actually derive this equation, your the distance equals your v1t plus 1/2 at squared. Which is your distance again, that's your delta x that we just derived. Now, when you actually start from rest, that means your velocity, your initial velocity is 0, initial velocity is 0, that means your distance equals at squared over 2. So let's go ahead and look at another video. Now notice it's going on an angle. So what can you say about the magnitude of the velocity of the glider? Okay. So is it going at a constant rate, increasing rate, decreasing rate, or can't tell? I'm gonna give you a little moment to think about that. You can go ahead and play the video again if you want to. Let's go look at, I'm gonna go ahead and start the next video after that. The distance between the dots is getting bigger, that means it's accelerating. Now we put a different angle and a steeper angle. Notice the longer it is, the more the spacing between the dots go up, so it's accelerating at a different rate. All right, now, let's do this question. How far did the car in the last example travel before coming to stop? With that one that whose brakes can produce an acceleration of minus 6 meters per second? Again, traveling at 30 meters per second, we had that time of 5 seconds. So let me go ahead and write this down. Example 2.6, I guess. I don't know why it's 2.6, but we're gonna go in with my slide. So be 2.6 example. So your initial velocity was 30 meters per second. We know we had the acceleration of minus 6 meters per second squared. We just calculated the t at 5 seconds. And we're looking for your distance. Now, we said that your distance equals your v1t from our equation earlier, plus at squared over 2. So this is going to equal to 30 times 5 plus minus 6 times 5 squared divided by 2. So both of these is going to be 150. Both of these, 25 times 6 is 150 divided by 2 is minus 75. So it'd be 150 minus 75. So you get minus 75. So you get 75 meters. That's exactly what we got. Now, free fall. I want to go ahead. We're going to be talking about gravity later, but I want to go ahead and touch base on it. Free fall is a special case of acceleration. Now, it was first noticed or developed, experimented with Galileo Galilei, which he went from 1564 to 1642, which he performed the groundbreaking experiment, which I'm pretty sure. So you got two balls that went on the Pisa Leaning Tower, and he dropped them both. Now, they both were different sizes. I think he got a cannonball and a pebble. Now, when he dropped them both at the same time, he found out that they both dropped at the same time. So he noticed that he found out that the higher the stone is dropped, the larger the speed of the stone hit the ground. You also realize the acceleration is acting on the stone is constant. That means the velocity is directly proportional to the time that the object has been falling. So basically, he noticed that the speed of the falling object depends on the time, not the object's mass. Now, if you neglect air resistance, all objects fall at the same rate. And that's where we actually talk about gravity. So the acceleration of gravity, which we give it a little letter g, and for objects in free fall, is going to be 9.8 meters per second squared. Now, this is the number we're going to be using the most. We're not going to be using a lot in the centimeter per second square or feet per second square, but I'll put it in there. It's 32 feet per second square, but we're going to be using 9.8 meters per second square most of the time. So, and again, we said that we developed that they are, let me just go ahead over here. So we said when at rest, when v equals 0, so we said your delta x, your d, which is actually going to be your delta x, which is your x2 minus x1. Okay, your d is going to equal to your v1t plus at squared over 2. Now, at first we said that this is going to equal to 0 for v. So that means your distance is going to equal to your at squared over 2. Now, when you talk about up and down, you're talking about height. So really your distance is nothing important, is height. We're talking about height, when you're dropping down free fall, we're talking that only extension is going to be on it is your gravity multiplied by time squared over 2. So your height is 1/2 gt squared. So if you say a stone is dropped from a bridge strikes the water 2.2 seconds later, what is how high is the bridge above the water? So for example, let me actually get a new this example. Your time is 2.2 seconds, and you're looking for your height. Now you know your height is gt squared over 2. It's gonna be 9.8 times 9.8 times 2.2 squared divided by 2, and that should be equal to I got 23.17 meters. which is they rounded up to 24 meters. Now, actually, let me go ahead on this one. Now, we actually went through different variables. We went through your distance, which is your delta x. We went with your distance, which is your delta x. We went we defined velocity, time, acceleration, and initial velocity. Velocity. Distance. Final velocity, time, acceleration, and initial velocity. Let me go ahead and write this as GI. I have no idea why I put an O in there. Fine. So we define the first equation as V2 equals V1 plus AT. So if you do not have the distance, use this equation. The other equation that we developed was your D, which is equal delta X, is going to equal to your V1T plus AT squared over 2. Now you use this equation. Again, notice we don't have final velocity. Now, the other three variables, I'm not going to go through that whole algebra of developing those three equations, but I'm going to go ahead and write the other useful equations for kinematics. So your final velocity squared is going to equal to your initial velocity squared plus 2a x final minus x initial. Now use this one if I don't give you in the question the time. If I don't give you the acceleration, you're gonna equal your d, which is gonna equal your delta, is gonna equal to your 1/2 average velocity, which is vi plus vf times t. And then the last one, if I do not give you the initial velocity, the last kinetic equation is gonna equal again your d equals your delta x, which is gonna be your final velocity multiplied by t minus at squared over 2. And those are your 5 kinematic equations. So that's number 1, number 2, number 3, number 4, and that's your number 5. Now let's say you have a graph of, let's say you have a graph of an acceleration. Actually, let me use a different color on that. Let's see, you go increase, go steady, and decrease speed. Okay, and this is your V versus T graph. Now over here in this area, your V is constant. Your velocity is constant. And you know that your acceleration is your change of velocity over your change of time, which is going to be your dv over your dt. That means your dv, change in velocity, is going to equal to your a dt. Now you have a ununiform object over here, so you're going to be using calculus. That means your v2 minus v1 is going to equal to your integration from t2 to t1. I mean, sorry, 2. From initial to t1 to t2 final, a dt. Go ahead and label this also on here. So this is your T naught, T1, your T2. So you got your acceleration. So this is going to be, put extra shell there. This is going to be the integration of the acceleration from T1 to T2 dt. And that's where your AFT is at. Same thing. If you're talking about your distance, your delta x is going to be your integration from T naught to T1 vt, where you, again, your v is your dx over your v is your dx over your dt, and your v is going to equal to your limit from delta t to 0, delta x over delta t, which is going to equal to dx over your dt. And again, solving it, and you get, again, your and again, you get that when you solve it, you get your integration of delta x equal d dt. So let's go back over here. We went sidetracked a little bit. We talked about the kinematic equation. We're going to see those in a little bit. Now let's go back over here. You got a stone to drop from the bridge, strikes the water at 2.2 seconds. Later, how high is the bridge above the stone? And that's the one we just solved for 2.424 meters. Now, an apple is dropped from a window 20 meters above the ground. How long does it take the apple to reach the ground? And what is the final speed? Now, what I'm going to do, I'm going to let you all, let's go ahead and solve it. So you got your height is 20 meters. Let's go ahead and solve this really fast. Your height is 20 meters, and you're dropping it. So you're looking, how long does it take for the apple to come down? So you're looking for part A, you're looking for your time. That means, again, your h equals your at squared over 2. That means your t is going to equal to your 2h over, now your a, that's going to be your g, your gravity. So 2h over g square root, which is going to equal to 2 times 20 divided by 9.8. So I got 4.08 meters. Now I think we got a problem over here. 2 times 20 divided by 9.8, this should be 4, not the 2. So make sure to correct that. Now the second part of the question, what is the final speed? Your final speed for part B equal GT. Actually, just from our go up over here, kinematics equation. Now we don't have, for this one, we do not have, we need the final speed. So we use, here it is. We don't have the distance. The final speed equals V1 plus AT. And again, you should go from rest, so your final speed your initial speed, because you dropped your initial speed, is 0. That means your V2 equals AT, your final speed, which is going to equal to your 9.8, multiplied by your time, which is going to be, again, is going to be your 4 minutes, your 4 meters, so it should be 39.2 meters per second. Again, here, we need to correct that now. So let me go. Actually, I just looked at this, we had a little mistake, so we forgot to square root the answer, so the actual answer, I was wrong, I actually looked at my answer again. It's actually 2 meters. We forgot to square root the answer, so I got 2 meters, which means that this one, 9.8 times 2, and it's gonna be 2 times 9.8, 19.6 meters per second. So I was wrong, I made a little calculation mistake. All right. Now, an object thrown horizontally has a vertical acceleration of 9.8 meters per second squared and a constant horizontal velocity. The trajectory is a curved path. In the absence of air resistance, the curve is a parabola. Now, when you actually throw that, again, you get your horizontal axis, your vertical axis, and that's going to be your resultant. Go ahead and do this video over here. Which will strike the ground first. Let me go ahead. So the ball that will go straight downward, that goes sideways, both will strike the ground first at the same time, or any of the above. Go ahead and think about your answer. Go ahead and play the next video. Ready? Go ahead and play the next video. All right, wonderful. Now let's look at the next one. Now, what angle can you throw something to go the furthest distance? So let's look at the balance. You have 15, 30, 45, and 60. What do you think? Go ahead and think about it, and then press pause and then play the other video. Let's look at the other video. 60 degrees. That's 75. Which one do you think it is? So the maximum range was a 45-degree angle. All right, now let's talk about a little bit about friction. So this talks about friction. So in real life, friction forces are almost always present. Now, the direction of friction forces always oppose the motion. Now, friction is bad because it dissipates energy, and it's good because it allows you to run, roll, stop, and do whatever you like. Now, there's two types of friction. Your sliding friction and your static friction. Let me go ahead and play this. Keep your eye on the red thing. When he moves it, it goes down. The sliding friction is going to be less than standing friction. Now, let me go ahead and do the other one. The board. Do you think you need more force or less force when you put the board on a side and try to slide it? All right, go ahead and think about your answer. And let's look. See? Yeah, so for instance, if you drag something on the side or upside down, it will still be the same amount of friction on it. So we said the required force will be the same. So forces of a sliding friction is much less than the force of the static friction. Friction between two solids does not depend on the surface area in contact. The friction can happen even between surfaces that are not solid. For instance, it can happen between liquids, gases, etc. Now, different materials have different friction to it. So let's look at this video over here. Notice the rubber is like glue. This has the hardest holding surface, frictional surface. That one was 18 degrees. This is smoother. The wood is a little smoother, so it's at 22. Then you got your sandpaper, which is gonna be, you have about 25 degrees, and like we said, the rubber is just like glue, so that's gonna be at 50 degrees. Now, air resistance prevents a falling object from reaching the full speed produced by acceleration of gravity. Air resistance increases with the speed of the moving object. So let's go ahead and look at another video. Now, why would they fall differently? Think about that for a second. Let's look at the next one. Notice that the coin is falling faster than the paper. Notice that they're both falling at the same rate, the coin and the piece of paper. So which one is the following is true? Objects fall faster in the air than vacuum. And air lighter objects fall faster. All objects fall in the same rate in the air. All objects fall in the same rate in the vacuum. We just saw that. So all objects fall in the same rate in the vacuum. So now your terminal velocity is the maximum speed of a falling object obtains when the force due to downward acceleration of gravity is balanced by the upward velocity of the air resistance. The terminal speed of any object depends on the object's size, shape, and mass. Now, kinematics, that what we're doing, deals with the concept that are needed to describe motion. Dynamics deal with the effect that forces have on motion. Together, kinematics and dynamics form a branch of physics called mechanics, and that's what we're doing. And again, we just talked about this. Your distance is going to equal to your initial position minus your final position minus your initial position. So if you have your initial is 2 and final is 7, that means your delta x is going to be 5. If you have your initial at 7 and your final is 2, so your distance is minus 5. Now, we talked about the average speed, which is your distance over your time, which is going to be your meters per second. How far does a jogger run in 1.5 hours? If the average speed is 2.2 seconds, again, your distance is going to be your velocity multiplied by the time. So between 2.22 times 5,400 is equals to 12,000 meters. We also talked about the average velocity, which is your displacement over your time. So your delta x over your delta t. Here is that question. Go ahead and pause the video and try to answer the question and see if you get the correct answers on it. Now, we talked about the instantaneous velocity, which indicates how a car moves and the direction of the motion for each time, which is going to equal to your limit from delta t to 0, delta x over delta. Now, we also defined the acceleration, which is your delta d over your delta t. So in this example, your initial is 0, initial velocity is 0, your final velocity is 260, and your t initial is 0, your final time is 29. So your acceleration would be 29 divided 260 divided by 29, which is going to be your 9 kilometers per hour per second. We also derived the equation for the displacement, And we talked about, we actually talked about all four kinematics equations. We went through all that right now in my notes. So your equations are as follows. So it depends on what missing quantity that you're using, that you have, you use the equation that's corresponding with it. And that should close chapter 2 for physics 111. If you have any questions, let me go ahead and stop sharing. If you have any questions, just call me at 256-348-1480 or email me at abunaem@uah.edu.